So Robert Boyle did an experiment a long time ago with gases, looking at the relationship between pressure and volume. And so he had this J tube.
Why are they called that?
Why do you think? Because it's shaped like a J. There's also U tubes. And U tubes are shaped like U's, and this side would be the same length. Yeah. Maybe there's a V tube too, but those would be harder to make. Yeah. The original U tube wasn't nearly as exciting. So this is a J tube. It's closed on one end. So you have some gas in here, and he just used air, because, hey, that's easy. He just used air, and so he put some mercury in here. And we look at this and we see that the pressure inside, where this gas is a little higher than the atmospheric pressure, because it's pushing down on this mercury and it's pushing that side up. So the difference in pressure is equal to the height of the mercury here. Now, when you add mercury to this, you're adding more mass that's pushing down. And so it's going to push down, but it's not going to completely fill this up because that gas is in there, and the gas is occupying space. Question?
Did everybody just start using mercury after some point? After a certain scientist was doing things with mercury?
I don't really know. The history of chemistry, I think, you could probably you could spend years studying the history of chemistry, and I personally think it would be really interesting. I just wouldn't want to be tested on it, but I don't have time to do stuff like that. They used mercury because of its density, and so you can get you can do things like this in smaller containers than you can do with water. You can do this with, and mercury's fun too, and I don't know that they realized how toxic it was. People used to drink out of pewter cups and stuff too, which had a lot of lead in them. And so it wasn't a coincidence that a lot of the royal people went insane. It's because they were wealthy and had the more expensive leaded crystal, and a lot of the stuff that they ate their food out of had lead in it. And the poor peons who were using tin or wood or whatever, their fingers, they were fine, but the rich people were poisoning themselves. It's a little bit of justice, yeah. So you can do this with water. And in fact, there's a lab I do at COS where we use water. And the good thing about water is if you have a little change in pressure, you get more of a change in the heights. So if you're looking at pressures that are only slightly different, that works really great. But if you're trying to put pressure on this gas and compress it, then you'd have to have a really big tube of water. And so that gets...
Would you like blow the tube out?
No, it wouldn't, unless you made it really thin or something. And what's interesting is the diameter of the tube doesn't matter. Unless you get to a really, really tiny, then you get some issues with capillary action and stuff like that. But if you made this tube twice as large in diameter, it would be exactly the same. The difference in heights would be exactly the same.
Didn't you try to do the same thing as the first guy that you talked about?
Well, the first guy did the inverted tube in the dish. And then I ended up kind of talking about this, but Torricelli didn't do this. We were talking about manometers.
And does this matter?
Oh, okay.
What if you were at a higher elevation? Would you still get the same differences?
If you were at a higher elevation, the difference would be different. Does that make sense? The difference would be different. Because what you're measuring here is the difference between the external pressure, which is atmospheric pressure, and the pressure inside. And so if you take this up into the mountains where the atmospheric pressure is lower, then that's going to affect the heights. But they added mercury, Robert Boyle added mercury, and found that caused the gas volume to be smaller. So he could measure the volume and he could measure the pressure, and then he would graph data, because that's what scientists do. So here's an example of his observations. So when the pressure, and this is inches of mercury. I don't know that they had the metric system yet. I'm pretty sure they didn't. So 29.1 inches of mercury, the gas had a volume of 48 cubic inches. When you increase the pressure to 35.3 inches of mercury, then it had a volume of 40. And so what he's doing is he's adding a little bit of mercury, measuring the pressure, measuring the volume. Add a little bit more, do it again. Add more, do it again. Over and over and over again. So you get these numbers. And you look at those numbers and you're like, that's interesting. You can see that as the pressure goes up, the volume goes down. But you can't see the relationship of that just by looking at the numbers. And that's why we use graphs, because graphs help us to see the relationship. So I'm going to show you the graph. So here's the graph. So at high pressure, the volume is low, and at low pressure, the volume is high. And that's a kind of a curve. And so then you can do math things with that. And if you take the pressure times the volume, you get this number, 1396.8. And if you go through and do all of those and multiply them, these are pressure times volume. Well, there's not really a trend of that going up or down, is there? And if you look, these are all three significant figures, well, except for this guy. So if we round these numbers to three significant figures, look at that. They're very much the same. It's very cool. So the pressure and the volume are inversely related. When one goes up, the other goes down, and it's a direct relationship. They really should give us another graph here, and I'm going to make one. So if you graph pressure versus 1 over the volume, you get a straight line. And the equation of a line is y equals mx plus b. Well, this one goes through 0. Pardon me? It's math. Yes, it is math.
Yeah, there you go.
So y equals mx plus b. B is the intercept. M is the slope of the line. Well, if the intercept is 0, y equals mx. So y divided by x equals a constant, the slope. Scoot over here. I said that x was 1 over v, so we've got y divided by 1 over v. That equals pressure times volume equals a constant. Cool, huh? This is how science works. So they make observations, adding, mercury, and this gets smaller, and that's a good observation. But then measuring it, and measuring it at different volumes and different pressures, and then looking what's the relationship between these things. Most things have a mathematical relationship between them. Then you just have to figure them out. So you'll look at the graph and you say, well, that looks, what if I graph 1 over? Or what if I graph this to raise to the power, or different things like that. What you want to do is you want to get a straight line, because then you've got an equation and you can get somewhere with that.
Do you say that it increases proportionately?
It's proportional, yes. Because some things increase, but it's not proportional. Like
Because it's
taxes.
equal. It has to be proportional.
Yeah. So like taxes, as your income goes up, the amount of tax you pay goes up. but it's not a straight line because their tax code's really complicated and there's different brackets, and so it kind of jumps around, and it's not necessarily a direct proportionality. So Boyle's law says that pressure and volume are inversely related. Yes?
Okay, but at some point in these experiments, there's gotta be like a breaking point, right?
There is a breaking point, yes.
So how does that still work out with the math? Because
Well, it doesn't. So Boyle's law works within a certain range of conditions. Because if you compress the gas too much, it liquefies. Well, then it's not really a gas law anymore, is it? Like when you go and barbecue on your gas grill, in that tank, that's liquefied propane. They put the propane in there, and it's under so much pressure that the particles are forced together to become a liquid. It is awesome.
But it's really a gas.
But it wants to be a gas. And a butane lighter, and some of them you can actually see the butane in it. It's liquid, right? But when you flick the bic, is liquid coming out? No, it's letting gas out. But because it's compressed in there, you can have a lot more of it, and it lasts a lot longer. You can get a lot more use out of it. So we compress gases so that we don't have to, haul around giant things of gases.
So once free, it turns itself back into a gas? Like free
Yes.
or that not?
And we're going to understand why it does that.
Well, that's just cool.
It's very cool. It's crazy cool. So we kind of already covered this. So the pressure times the volume is a constant for a given sample of gas. Now, if you had a different gas, a different amount of it, different temperature, it would be a different constant. But if you have one sample like he was doing, and you're just changing the pressure and allowing the volume to change, then it's going to be a constant. I should make this illustration a little bigger, but so here we have a sample of gas, and if you count the little balls in there, there's the same in each. So it's the same gas, and here we've got a lid. This is like a cylinder with a lid that can move up and down. So if we have 1 atmosphere of pressure on here, this has a volume of 1 liter. And the temperature for all of these is the same. If you double the amount of pressure, the volume will be cut in half. If you quadruple the pressure, the volume will be 1/4 of what it was before. That's the direct inverse proportion. So one doubles, the other cuts in half. Any questions? Oh, I thought I got rid of all the animations. Apparently I did not. So that is the mathematical expression of Boyle's law. And I am not going to quiz you on these guys' names. I use their names because the book uses them and because we should remember these people. They did some really, really important stuff. I want you to be able to use the equation. I will give you these equations. Okay, that's one of the differences between Chem 3A and Chem 10. I don't want remembering equations to mess you up. We're going to focus on learning how to use them. And then when you get to 3A or 1A, then you'll have to remember them. So the pressure 1 times volume 1 equals pressure 2 times volume 2. So let's do an example here. A sample of helium gas occupies 12.4 liters at 23 degrees Celsius and 0.956 atmospheres. What volume will it occupy at 1.2 atmospheres, assuming that the temperature stays constant? That sounds complicated, doesn't it? This is a gas problem, and what we need to do is organize this information, and the best way to do that is to make a table. We're going to have one condition and a second set of conditions. So make a little sketchy table there, and then go through the problem again and write things down. So 12.4 liters. So 12.4 liters. Liter is a unit of what? Volume. So I'm going to call this column volume. And 23 degrees Celsius, we'll stick that in there. That's the temperature. and 0.956 atmospheres. Atmosphere is a unit of what? Pressure. It's okay. We just learned that one today. What volume, okay, that's the question, will it occupy at 1.20 atmospheres? Well, let's put that in the same column with the other pressure, 1.20 atmospheres. Assuming the temperature stays constant, okay, so the temperature is the same. And the question is, what's the volume? We have one empty square here. So we're going to call that V2 because it's in the V column and it's in the second row. The temperature is staying the same, so we can ignore that. So we just learned about Boyle's law, P1 V1 equals P2 V2. What are we trying to solve for? We're trying to solve for V2. Actually, let's do this color. So here's V2. We need to rearrange our equation to get V2 by itself. So I'm going to divide this side by P2 because P2 over P2 is 1, right? Now, if I did that to one side of the equation, I have to do the same thing to the other side. Divide by P2. Now I'm going to rewrite this, and that's not what I wanted to do. V2 equals P1 V1 over P2. Now, if you have trouble rearranging equations, that's pretty basic algebra, but I would not be surprised if at least half of you are a little sketchy on that. Please get some help because it's not going to go away. Okay, Math Center, tutor, ask your neighbor, or ask me. That would be a great idea. So we've got our equation, and we're going to plug our numbers in. Pressure 1, we've got everything organized in our table, 0.956 atmospheres, and volume 1 was 12.4 liters, and pressure 2 was 1.20 atmospheres. Double check that your units cancel out like you want them to. So we've got 0.956 times 12.4 divided by 1.2. So that is 9.88 liters. Does it make sense? We increase the pressure, we would expect the gas to get smaller. Okay, test on Wednesday.